All right, today is the second day of section 8.4 Trig Substitution. So just a quick summary and comparison. All right, so remember when we see this square root of a squared minus u squared, we've got our triangle. We're going to make that substitution. U is a sine theta. Square root of a squared plus u squared. We'll use u is a times tangent of theta, and then square root of u squared minus a squared, our triangle, and we'll let u be a secant theta. All right, so we're going to go through just two examples today, kind of working through this, and we'll see where it takes us. So let's go ahead and zoom to this first example here. All right, now I see 10x minus this minus x squared underneath a radical. Now, that doesn't look like anything from up above, so what can we do? Well, what we can do is we can make it look like something from up above by completing the square. All right, so let's go through the completing the square process. I'm just going to rewrite it, factor out a negative. So negative times x squared minus 10x, and remember, take this middle term, divide by 2, square it. And what we really did was we added a negative 25, so on the outside we have to add the opposite. So we're really adding positive 25 over here. And then we can just rewrite it factoring this guy, and we really get 25 minus the quantity x minus 5 squared. So now we're just rewriting what's underneath that radical so it looks like something we can deal with. Okay, now in this case, we don't have, or we don't necessarily need to make a trig substitution, okay, because there's nothing else going on, right? So we don't necessarily need to do that. So we can just make a U-substitution in this case, all right? So if we let a be 5, that means u is going to be this x minus 5. Taking the derivative, we get du as dx. So when we go through, all right, we know that we're just left with 1 over this square root of a squared minus u squared. Well, that's the arc sine or inverse sine of u over a. Don't forget your plus c, okay? And then substituting back, we get that final answer. Now you might ask, well, why didn't we use this a trig substitution? Well, we certainly could have. All right, and that's kind of a longer way to go about this type of problem. So I'm going to show that over here. We end up getting the same answer, okay, obviously, but it's just a little bit longer to go through that route, okay? So we still have to go through the completing the square aspect of it, so that amount of work doesn't change. And now, again, we can let a be 5, u is this x minus 5. And then using that trig substitution, if u is a times the sine of theta, then x minus 5 equals 5 sine theta. So x is 5 sine theta plus 5, all right? And then dx is going to be 5 cosine theta d theta. So now we can go ahead and use that trig substitution, so 5 cosine theta d theta for dx. And then I factored out a 25 right away. When we square these guys, when we square x squared and we square a, we can factor out that 25. 1 minus sine squared is cosine squared. Square root of 25 is where we get 5. Square root of cosine squared is cosine. So this all ends up canceling out, and we're just left with the integral of d theta, which is theta. But now we have to do some more work and figure out, well, what is theta actually equal to? So since from up above here, we know that sine of theta or 5 times the sine of theta equals x minus 5. So sine of theta equals x minus 5 over 5. We can solve for theta by taking inverse sine of x minus 5 over 5 and then substituting back in. So there's a lot more side work to do with this example. All right, is it wrong? No, but if you can see the other route, it's much more efficient. The second example, we have a cubic polynomial over a quartic, but what we might notice is if we're able to split this numerator up, so maybe if I cut it off right here into two separate integrals, we're going to be left with the integral of x cubed plus x over our denominator, plus the integral of 1 over that denominator. Now, why would I do that? Well, what we should notice is we can factor this numerator by pulling out an x. We can factor that numerator, it's a perfect square trinomial, and then things will cancel a little bit nicer over here on this first integral. Over here, I'm just going to factor the denominator, okay? So as we continue to clean up that left side, let's see where that takes us, okay? All right, so the x squared plus 1, that's going to cancel, and we're going to be left with the integral of x over x squared plus 1. This is going to be a straight U-substitution. If we let u be x squared plus 1, then du is 2x. So we can integrate this piece. All right, so I'll come back to that. Let's go ahead and focus on this right here. I can't necessarily do a straight U-substitution because I'll be left with x still. So I can go ahead and let a be 1 and u be x. So then I can use the fact that I see this a squared plus u squared, all right, and we can use the tangent of theta. We can make a trig substitution, and it's okay that it's not underneath the radical, all right? It still works. So if that's the case, then dx is going to be secant squared theta d theta, all right? And thinking about it in the long run, you know, we've got theta is equal to inverse tangent of x, and then we also have our triangle because we'll probably need that when we substitute everything back. Okay, so going with that, all right, dx is secant squared theta d theta, so we're going to make that substitution. X squared is tangent squared plus 1, and we're squaring that whole quantity. Okay, now keep in mind, we can integrate this left side hopefully relatively easily, okay? All right, so now as we go through, remember tangent squared plus 1 is really secant squared. That's that trig identity, okay? So now secant squared squared is secant to the 4th, all right? Okay, over here we're just integrating 1/2 ln of the absolute value of u, all right? We're cleaning up this guy, and we end up with the integral of 1 over secant squared theta d theta. Substituting back, we have 1/2 ln of x squared plus 1. I can drop the absolute values because this will never be negative, okay? All right, so now again, I'm just going to focus on this, and this first guy is going to just come on down for the ride. All right, so another way we can rewrite 1 over secant squared is cosine squared. Okay, well, remember our rules. If cosine is even, we need to make it odd. Okay, so we can use one of those trig identities to say, oh, remember, cosine squared of theta is really 1 plus cosine of 2 theta over 2. So we're going to substitute that back in. We can split this up into two integrals now. The integral of 1/2 d theta plus 1/2 cosine of 2 theta d theta. Okay, well, we can go ahead and integrate cosine of 2 theta, right? Okay, so we can integrate that, and we get 1/2 sine of 2 theta. Don't forget the plus c, and this guy integrates as theta over 2. Now, we can't make this substitution yet or use our triangle with sine of 2 theta, so we need to use yet another trig identity. Okay, so this is probably one way back in your brain, but bring it out. So sine of 2 theta is really 2 times the sine theta cosine theta. So this will allow us to then use our triangle that we created up above to then substitute back in. Okay, now remember from up above as well, we already found what theta was equal to. So that's this piece up here. Okay, so we're making our substitution. Instead of theta over 2, we have arctangent of x over 2, or inverse tangent. Okay, we made that trig identity substitution, and now we're just cleaning things up. All right, now I notice everything has a 1/2, so we can pull that 1/2 out. All right, we're left with the ln of x squared plus 1 and inverse tangent of x. And now sine of theta, this is where we're going to use our triangle up above. Sine is opposite over hypotenuse, so x over the square root of x squared plus 1. And the cosine of theta is adjacent over a hypotenuse, so 1 over the square root of x squared plus 1 plus c. And now we're just going to clean this part up. The square root of x squared plus 1 times the square root of x plus 1 just leaves us with a denominator of x squared plus 1. All right, and here we have our final answer. So this was quite the doozy. It has a lot of information in this problem. One, splitting up our numerator, all right, to create two separate integrals. One that's a U-substitution makes things easier, and then one where a trig substitution makes things easier, and we carry out those operations, reminding us of those trig identities here to help us out along the way. If you have questions, let me know. See you next time.